We good?
Mm-hmm. Might be low on battery though.
Oops. Okay. So up until now, we've looked at how C code gets translated into PEP8. But obviously, you can take and just write your own programs straight in PEP8. And what we have here on the next couple of pages isn't a program that was not translated from a higher level language, from a C or whatever. This was just programmed entirely in assembler. So if we look, you get some inputs. It's loading into loading the accumulator, doing a comparison, doing a branch, and if we look at this, it's very very random. I mean, if you look on on page 33, you look at line 3F. There's a stop. If you go to the next page and you look at line 4F, there's a stop. There's a stop at line 7D, and then another one at E4. Now, is this legitimate? Yes, this is legitimate assembly code. Now, the problem with this is, if we take a look, if we on page 35, if we take a look at the structure of this, and the left side is the structure of this code. You see that we've got there are branches all over the place, and if you had to try to follow this, it would be a mess. Well, this type of code, which it's called a couple different things. It's called unstructured code because there's it's really all jumbled up, but it's also called spaghetti code. Mostly because if you take a look at how this flow is, you've got lines all over the place crossing each other, and it looks like a bunch of spaghetti. Now, in this case, we're talking about assembler programs, but the term spaghetti code is also used for high-level language programs. And basically, these are ones that jump all over the place and really don't have a very good structure to them or flow to them. Now, there was back in the 60s and into the early 70s, there was a debate over how code really should be written. And there was a theorem put out by Boyle and Jacopini in 1966. It says, any algorithm containing gotos, no matter how complicated or unstructured, can be written with only nested if statements and while loops. So back in some of the early languages, goto was a legitimate command. Now, the problem with gotos is, again, it would work, but the code was pretty much it was very hard to follow. It was very unstructured. So again, so these guys came out and said, basically, you know what? we don't have to use all these go-tos. We can take and make the code, more structured, more easier to read, more easy to deal with. And they said, again, anything that you can do with go-tos, you can do with nested ifs, and with while loops. Now, there was a gentleman by the name of Edgar, I think it's Dijkstra, whatever. He was Norwegian. He's a big figure in programming. He died of cancer a couple of years ago. But he went out and he looked at this whole thing about structured programming, and what he came back with, he wrote an open letter to the editor, and part of that was the quality of programmers, the quality of what a programmer does is a decreasing function of the density of go-to statements in the programs that they produce. Most recently, I discovered why the use of go-to statements has such disastrous effects, and I became convinced that go-to statements should be abolished from all higher-level programming languages. So again, what he was advocating is what is called more structured code. And with structured code, it is very easy to read. It's very clear to see where things were happening. Now, I will say that there were some languages out there, such as just plain old BASIC, that did rely on go-tos. However, even within that, and my first language in college was VAX BASIC, and the instructor said there are going to be occasions where we're going to go-tos are going to be needed, just because there's no other way to do it in the language. But even in that, you had to have some structure to it so that it was easy to follow, both for yourself and for whoever is looking at it. Who's done some coding? Okay, everybody has. Have you come back? Have you written some code maybe for class and not thought about it for a week and come back to it? Okay. How many of you said, "What the hell is this"? Anybody? No?
I comment thoroughly.
Huh? Ah! Okay, you're up.
Only if I'm not coding in a state of mind.
What's that?
I
Yeah.
don't know how to say.
Anyhow, have you ever come back to it after a month?
You kind of have to look through it.
Huh?
You kind of have to look through it and follow it again.
Right. You have to follow it again. Even if it's, there's stuff that I wrote even like a year ago that I have to go back and look at, and I can't remember what this thing, why I did what I did. If it's spaghetti code, it is that much harder to figure out. If you got, if you got a bunch of go-tos and everything in there, it's even for you, even if you wrote it, it's going to be very tough to follow. So that's why the concept of actually writing structured code is so prevalent today. It's simply so that it's easy, if you got to go back to it, or somebody else has to go to it, it's easy to understand, it's easy to follow. All right? So that was kind of a little pleasant little trip off the path for a couple of minutes. Okay, last thing we're going to look at tonight before we, other than taking a look at the PEP 8 simulator, is basically we want to look and see when we call subroutines, what happens? How does that get translated into assembly or into assembly? So, in order to do this, we've got another instruction that is call. And basically what this does is it really is going to do two things. It's going to take and push a return address onto the runtime stack. And it's basically then going to do a branch. I think it's a branch. So with the call, it pushes the address onto the stack and then basically does an unconditional branch to another spot in the code. So it pushes the the return address onto the stack so that once the subroutine is done, the program knows where to continue or how to continue. So again, when we call a subroutine, we push an address out onto the runtime stack. We go out, the subroutine gets run, and then when that subroutine is done, there is a new instruction called RET that takes a value n. And basically what this will do is it's going to pop the storage, it's going to pop the storage for the local variables and the return address off of the runtime stack. So any of the variables that were used in the subroutine, they get popped off, and the last thing that gets popped off is the address for the next command. So let's look at an example. So we have we have a C program here. We don't have any variables, so we're not dealing with the stack per se for variables. But what we're going to do is we're going to call the print try function. We're going to call it 3 times, and then end the program. So if we look at print try, basically it does 3 outs, 3 C outs, it outputs 3 lines, 1 star, 2 star, and 3 star. All right. So if we look at the assembler for this, and the example program is on page 40, the assembly is on page 41. So if we take a look at this, this is kind of broken up into 2 parts. So down here at the bottom, starting in line 1F, this is the code for main. And all that we're doing for main is we have 3 calls, and we're saying call print try 3 times. And if we go up to starting in line 3, we see it's basically 3 combinations of string out and character out. So the string out prints either 1, 2, or 3 stars. The char out or the char out does the line feed, moves it down. And then we come down And the last thing in here on line 15 is RET 0. So this is saying, okay, we're done, return, and the memory address is the first thing on the stack. So let's follow this through a little bit. And actually, let me see what the next. All right. So when we get down to line 1F, we've taken, we're going to do the call. So we said call, the first thing that it does is what? Anybody remember? So call is going to push a return address onto the runtime stack. And then return is going to take and it's going to pop it. It's going to pop that off. So when we come down to line 1F, we do call. First thing that it does is it pushes a return address onto there. Now, in essence, what happens, and if you look at page 42, what happens is before the execution of the first call, you got address 0022 in the program counter, and the stack pointer is pointing to FDCZ, and there's nothing in the stack. After we do the call, notice that the program counter got pushed onto the stack, and then the program counter, in this case, gets set to 3, which is the first line of the actual of print try. So really what happens when you do a call is wherever the program counter is pointing to, that's what gets pushed onto the stack. So, yeah, so now we've got 0022 pushed onto the stack. So when we go through the routine and we come down to the return command, the RET, if you look, and this is on page 43, before that execution, our program counter is pointing to location 16, line 16. Now, after that gets executed, the memory add, after that gets executed, when it executes, it pops the memory address off of the stack, and that goes into the program counter. So when we go for and execute the second call at line 22, what's going to get pushed onto the stack?
25.
25, right. So 25 is going to get pushed onto the stack. There's a branch to line 3. That code executes. You get to line 15, which is your return. So the memory address. So 25 gets popped off of the stack, put in the program counter, and that's the next instruction to be executed. So then when we do the third call, what gets pushed onto the stack?
28.
28. Correct. So again, that gets pushed onto the stack. Program counter gets set to 3. Print try does its thing. And with the return, 28 is popped off the stack and put into the program counter. And that's the next instruction to be executed. So in this case, it's stop. So really, what the call command is doing a couple of things that before were being done individually. With the call, it's actually allocating space on the stack for the memory address. It's pushing that out onto the stack. And what the return does is it both pops the memory address off of the stack, and it also takes and deallocates that memory off the stack. So really, again, that thing, the call is doing a couple of things. All right. This is where I'm going to stop this week. So next week we'll start on page 44, and we'll do a couple. We'll continue on and do a little bit more. But next week I want to take and do a couple of things with you. So, last thing before we get out of here is I want to take and I want to show you a couple of things, and I am going to give an assignment to be done for next week. So, like I said, I put an announcement out here, and there is a hyperlink on the word here. It says grab the newer PEP8 simulator here. So if you click on here, it's going to take you out to code.google, and this is the page for the PEP8. Over on the left-hand side, under Featured, this is where you can take and download the PEP8 simulator. Now, there is a Mac zip file and there is a Windows zip file. Obviously, you download the one for whatever system that you're on or that you're going to use. Now, like I said, if you don't have a laptop, like Lauren, Mr. Yop, and Alexander, you can take and download this onto your USB drive. I was playing with it over the break, and it works just fine off of that. Okay. So anyhow, so you download it, you unzip it, and in that unzip is just the executable and the license text. Now, back out on Blackboard, under course documents, there is a link for simulation software zips. And if you click that, there's a couple things in here. The second one is example program file zipped. So these are the examples out of the book.
If you're using the newer version, it's already got all the examples in the help.
Okay, I didn't see that.
Go ahead and run it, and it'll be under help examples. Corresponds to everything in the book.
Oh, examples? Wow, thank you. Okay, forget about that. Forget about downloading. So anyhow, there's stuff in here from back in chapter 4. So just to get the feel for things, you can select one of the examples out of here. So if I want to work with what was in Figure 5.26. So this is one of the examples we saw last week and one of the ones that we saw this week. And I guess you just say copy the source. Okay. Cool. So you got the code here, and as I found out through trial and error, you have to pre-populate your input. So you go to the input block for batch I/O, and in this case, we're just going to input 2 exams, so there's 2 values in there. And you can just take and run it, and it'll do its thing. But if you really want to see what is going on, you can take and run the debugger. So there's a straight green arrow for just running it. Next to that, there's a green arrow with like a little blue circle on it. Well, actually, it's a little bug. Now that I look at it, and if you click that, it'll take you into the debugger, and you can just step through each of the instructions. So I come down here, I branch. So I do my first input, and if you notice, you can see the stack down here. So I can see I've got 68 on the stack. And also, I can see what's going on in the CPU. So I can see my accumulator, I can see my index register, my stack pointer, all this other good stuff, including our status variables. So again, so you can just step through this and you can see the stuff that's going on. So we've loaded exam 1 into the accumulator, and then added the second exam, do the divided by 2, etc., etc. So you can step through this and you can see the state of the machine for each example. Okay? So, obviously you can't break anything, so go ahead and play with this. Now, what I would like you to do for next week, and some of you guys did this, so if you've